we continue our discussion of two-dimensional thin airfoil theory. In the previous video and the previous lecture, we talked about a starting vortex, how it forms from the trailing edge, from the upper surface boundary layer, gets dumped into the wake. It's got a strength of gamma counterclockwise. On the airfoil, surrounding the airfoil, you have a clockwise circulation, which is plus gamma. We talked about what happens right at the trailing edge. Then we made an observation that the flow smoothly leaves the trailing edge above and below. Therefore, there could not be any pressure difference at the trailing edge. Also, according to Bernoulli equation, the velocity magnitude should be also equal above and below. So this is the observation that Kuda made. So this is called a Kuda condition right at the trailing edge. The pressure is equal above and below, and the flow is smoothly leaving the airfoil trailing edge surface. If the airfoil is cusped, that means there's no included angle at the trailing edge. Upper and lower surface will have the same velocity magnitude, and they need not be zero. On the other hand, if the airfoil trailing edge has got a finite included angle, at least in an inviscid theory, upper surface will have one velocity direction, lower surface will have another velocity direction, so they cannot have two different directions, velocity. Therefore, the velocity magnitude would come to zero at the trailing edge. But in the real world, even if you have a finite included angle, because you have a boundary layer, above the boundary layer, the velocity vector has the same direction as the below the boundary layer on the lower surface. It's got the same magnitude. That means the pressure is same above and below, velocity is same and above and below, except the velocity is just outside the boundary layer, not right at the solid surface. Now we are going to start developing some of the theory. We'll do it in a couple of videos so that it does not overwhelm us, so that the videos are fairly short, 15 to 20 minutes each. So we're going to develop it for a general cambered airfoil at an angle of attack. So if you are interested in a symmetric airfoil, all you have to do is set up the cambered airfoil to camber to zero, then you get a flow over a symmetric airfoil. We already saw that an airfoil is made of a chord line. Then you draw a camber line around it, that's to asymmetrize it. Then you add a thickness to it. It turns out thickness does not produce any lift. Remember the Rankine half body, it was a very, very bluff body. It did not produce any lift. Rankine's full body, had a lot of thickness, but it did not produce any lift. Flow over a circular cylinder. Circular cylinder had as much thickness as much as its length, but did not produce any lift. Therefore, thickness simply disturbs the flow above and below the camber line by the same amount. So in the absence of camber line, it's disturbing the flow above and below the chord line by the same amount. So whatever happens on the upper surface is happening on the lower surface. Therefore, you don't get any lift. So in the thin airfoil theory, we neglect the thickness effects. We only include the camber line effects and the angle of attack effects. So for all practical purposes, rather than a stubby, thick-looking airfoil, it looks like a thin foil-like shape, almost like a piece of paper that's got a parabolic shape or some angle to it. Almost like the Wright brothers foils, pair of foils that you see, or a kites that you see. It's got a near zero thickness, but it's got some kind of a curved shape. So that's what we are going to do. Remember, the thickness of the airfoil is typically 12%, 15% of the chord. That means above the camber line, it's 6%, below the camber line, it's 6%. So thickness is small. So we are talking about a very, very small thickness. If you have a lot of thickness, if you don't want to neglect it, then we have to use something called the thick airfoil theory, or so-called panel method, that we will cover in a later slide. Xfoil, the software, uses panel method for modeling flow over airfoils. So this is definitely an approximation because we are neglecting the thickness effects. So this is a picture of an airfoil, the chord line. Then you build a camber line about the chord line. Then you add equal amount of thickness above and below the camber line to come up with the final airfoil shape. If you neglect the thickness effects, all you are left with is the chord line and the camber line. So we are going to solve the flow over this camber line at an angle of attack. So angle of attack produces asymmetry, camber line produces asymmetry. If there's no camber line, then this solid dark line will just fall along the chord line. You'll still get a lift if you have an angle of attack. So this is what we model. So it's an infinitesimally thin paper-like foil shape, and we are computing the flow around it. We have a pressure difference above and below that produces lift. So we are interested in what is that lift, and also how is that pressure distributed from the leading edge to the trailing edge, or how is the lift distributed from the leading edge to the trailing edge. What kind of rotating moments are caused by that pressure distribution, so that we can also compute the pitching moment, either nose up or nose down. So this is the picture. This is my chord line from left to right. This is my camber line, is the red line. This is the angle of attack. So if you use this coordinate system, by the way, X is the leading edge to the trailing edge, Z is perpendicular to it. Y is going into the plane of the paper. So if you do a right-hand coordinate system, the clockwise vortex is positive, nose up moment is positive. So anything that's clockwise is positive. So at the quarter chord point, later on when you compute the moment, if the airfoil rotates in the clockwise direction, bringing the nose up, then that's considered positive in our thin airfoil theory. The angle between this purple line, which is the free stream line, and the blue line, which is the chord line, is the angle of attack alpha. This is not a convenient coordinate system for us, so what we're going to do is we're going to rotate it clockwise to a wind tunnel coordinate system. Remember, in the wind tunnel, the flow is always coming from left to right, parallel to the tunnel axis. So we are going to rotate it. That means we are going to rotate the body, we are going to rotate the thickness and camber both. So the chord line has rotated, the camber line has rotated. So this is the coordinate system, or the wind tunnel coordinate system, in which we will do our calculations, develop our theory. Let's say there's any point here. Let's say the slope at some point is dz dx. So when you rotate something in the clockwise direction, what you're doing is you're reducing the slope by an equal amount. So if I take this, let's say this has got a 10-degree slope. If I rotate it clockwise by 1 degree, the slope will be 9 degrees. If I rotate it by 2 degrees, the slope will be 2 degrees. So clockwise rotation will reduce the slope, or make the slope, which is already negative, even more negative. So what we have to do is we have to take the original slope in the chord line based coordinate system, which is dz dx, where z is the camber line shape. Then after you find the slope, you subtract from it alpha, where alpha is in radians. This is the new slope at any point on this red camber line. So now let's continue. So this is the point P. The body slope there is dz dx minus alpha. Now this replaces our solid body because we have neglected the thickness effect. So it's a foil-like shape, but the flow is not crossing this boundary. It's still a solid surface. Just like a kite is a thin but impermeable surface. Wright brothers, their foils are nothing more than fabric. In the ship, sails are fabric, so there's no flow crossing through it. So the flow can only be tangent to it. There could be no normal velocity. So we say the flow velocity in the vertical direction, which is W, by the horizontal direction, which is U. If this is the flow slope, it should better equal the body slope. This was the original body slope before the rotation. This is the new body slope when we have rotated everything in the clockwise direction by the amount alpha, so that the free stream is parallel to the x-axis. Now, because the camber line is very, very small magnitude, dz dx is very, very small, z of x is typically 2 to 4% of the chord. So if the chord is 1 meter, the maximum deviation from the chord line to the red line is going to be 2 centimeters to 4 centimeters. Okay. Therefore, the slope is likely to be very, very small, like 0.01, 0.02, 0.05, something like that. Second, very small number. Alpha is also small. Therefore, such a small, mild camber at such small angle of attack is not going to disturb the flow at all much. Therefore, in the U direction, the disturbances are small compared to the free stream velocity V infinity. Therefore, we approximate the denominator U by V infinity. Then we take the V infinity to the other side. So the W component of velocity in this direction equals V infinity times dz over dx minus alpha. This is the linearized or approximate boundary condition. Why do we call it approximate? Because we have replaced the U, which was made of the free stream plus any disturbances caused by the body, by just the free stream only. So thin airfoil theory has got a number of approximations. We have neglected the thickness completely. We have also assumed the disturbances are small. That means the camber is small, the angle of attack is small. Now we go back to our treasure trove of building blocks. We had vortices, we had doublets, we had sources, we had sinks, we had free stream. We know we need free stream because otherwise we won't have any lift to produce. We know we need to have vortices because vortices produce lift in the case of a Rankine's lifting body. And pardon me, in the case of a lifting circular cylinder. Kutta-Joukowski theorem says lift is proportional to rho times V infinity times gamma. So we know among all the building blocks, V infinity or the free stream is a very important building block, and vortices are very important building blocks. But we know physically we don't have a one lumped vortex on the body. We have distributed vorticity on the upper surface and also on the lower surface. So we are going to distribute the vorticity as a difference between the vorticity on the upper side and the vorticity on the lower side. They are co-located on the same point. Upper side you have upper surface boundary layer, lower side you have lower surface boundary layer. So let's draw a box around it, take all the vorticity, lump it there. So we are going to do it point by point by point by point all over the chord, all over the camber line. So each one of these vortices is going to be very, very weak because we are taking a tiny slice of this camber line of width delta xc or delta x. Then we are going to capture the vorticity within that tiny box. So we are going to take the camber line, break it into small segments of length delta xc. So the vortex distribution d gamma over this short segment is some velocity-like magnitude times the length. Why did I split it this way? Because circulation is v dot ds, velocity dot product of width length. So it's got a units of velocity times distance. So if this has got a units of distance, this has got a units of velocity. So we distribute it all over the camber line. Okay. But that's not convenient because the camber line has got some funky shape. So it's very hard to analytically integrate anything along an arbitrary shape, things like this. Then we say, okay, this is only 2% or 3% above the chord line. So rather than putting the vortex at point P or point Q anywhere on this red line, I'm just going to put it immediately underneath it along the chord line. So this gamma dxc is not placed on the red line, but is placed along the chord line. So another approximation is again valid within the same order of magnitude analysis, assumes that the camber line, this maximum distance from any point on the red line to this blue line is 2 to 3%, 4% away. Okay, it's a very, very small deviation from the original blue line. By putting everything along the x-axis, we make our analytical integrations because we just need to integrate along a straight line instead of along some fancy curve like this, much more easier. So when they were developing these theories, remember this was long before computers. So between the First World War and Second World War, early times, Wright brothers didn't have any of these theories. They just had a wind tunnel. That's all they had to work with. So this is the model that they started with. So they took a free stream as a building block. They took tiny vortices of strength gamma, Xc, Dc distributed all over the chord line as the building blocks to model flow over an airfoil. Thickness was neglected, but the camber effects was kept. Angle of attack was kept. The angle of attack is showing up through the slope at any point P. Remember, the slope is original slope minus angle of attack. So let's stop here and we will continue with the video in a follow-on, a lecture in a follow-on.